We'll start with study guide 4. Self-test 4. Question 2. Bogana is sliding down a snowy hill on a toboggan. The mass of Bogana and the toboggan together is 41.2 kilograms. When she reaches a speed of 3.86 meters per second, she decides to stick her feet into the snow to reduce her acceleration. From the time she sticks her feet in the snow until she puts them back on the toboggan, she travels a distance of 29.8 meters and has a final speed of 6.79 meters per second. So let's start drawing the free body diagram. So here, this is the location where she had a speed of 3.86. So let me call this one V1. And here, her speed was V2. So this distance is 29.8 meters. This is 32.9 degrees. So this is the FG. FN. And this is the friction due to putting her foot in the snow. So we have the mass as 41.2 kilograms. This is my reference. Y equals to 0. Now the question here is asking me to, so this is 1.86 meters per second. This is V2, 6.79 meters per second. Okay. The question is asking, determine the amount of thermal energy produced by friction. So if we apply the conservation of energy for point 1 and point 2, in this case, the energy at 1 would equal the energy at 2 plus the thermal energy produced. So the conservation of energy is there. However, some of the energy has been transformed to thermal energy. So if I am to write now the conservation of energy, EP1 plus EK1 equals to EP2 plus EK2 plus the thermal. This is at point 2. The energy is already produced. So in this case, if I want to calculate the thermal, it is EP1 plus EK1 minus EP2 plus EK2, which means now I have kinetic and I have potential energy, gravitational potential energy here. However, here I only have kinetic energy because this is my reference now at y equals 0. So the potential energy will be 0 here. So in this case, EP2 is 0 because that's my reference. So W thermal is EP1 is mgy1 plus half m v1 squared minus half m v2 squared. So W term is, this is 41.2 times 9.8 times the y1. Y1 is the height from here to here. So if this is my y equals 0 and this is my positive y, yeah, then this height is the 29.8 times sine 32.9. So this is 29.8 and sine 32.9 degrees plus half times 41.2 d1 squared, which is 3.6 squared minus half times 41.2 times 6.79 squared. So this is y1. Which means W thermal is 535.5 plus 307 minus 9.9.74 equals to 5892.76. So this is the thermal energy produced, and we've seen earlier that this equals minus the friction energy, which is a lost energy. So this is a produced energy. That's why it is positive. Now, if we want to calculate, which is basically B1 now, B is asking determine the force of a friction acting on Borgana and toboggan. So in this case, we know that Fk equals, in this case, minus thermal is minus 5,892.76 joules. Now, if you go back to here and try to just redraw here to be clearer. So this is so we have here the Fn, we have the Fg, we have the friction, angle here at 32.9 degrees. Okay. Now this force is responsible for the friction, and if you want to calculate that force due to this energy that is being dissipated by the friction, then it would be WFK. Now notice that the displacement, this is the direction of the displacement vector, which basically making 180 degrees with the friction force. That's why when I put the work for the friction, K delta R cosine theta, here my theta between the, let me call this one delta R, displacement, the angle between those two is 180 degrees, and that's why this one becomes -1. So I have minus 5,892.76 equals to Fk delta R is 29.8 minus 1, in this case 5,892.76 divided by 29.8 is, okay, so let's move on to the next question. Next question is from the textbook 733. A girl pulls a large box of mass 20.8 kilograms across a horizontal floor. She is exerting a force on the box of 95.6 Newton inclined at 35 degrees above the horizontal. The kinetic friction force on the box has a magnitude of 75.5 in Newton. Use the work energy theorem to determine the speed of the box after being dragged 0.75 meter, assuming that it starts from rest. So if you want to draw the free body diagram here, so this is the friction. Fn, Fg, F, 35 degrees. This is the 0.1. This is 0.2. So we have the mass as 20.8 kilograms. We have the force as 95.6 Newton. We have the friction, kinetic friction as 75.5 Newton. We have delta R as 0.75 meter. My coordinates are x, y. Now, if I want to calculate the speed here, first of all, I would like to calculate the net force that is responsible for the work, which is basically, I will be projecting this Fx, and then I will say F net x equals to this Fx, which is basically F cosine 35 degrees minus Fk, or F net x as 95.6 minus cosine 35 degrees minus 75.5 F net x equals to 2.81 Newton. So this is the net force that is doing the work here to take that box from rest, which is basically here I have V1 equals to 0, and V2, that the one that I want to find, is unknown. So this is the work, this is the force that is doing the work. In this case, I can apply the work energy theorem here, where basically W equals to delta, the difference in the energy between 0.2 and 0.1. Since the potential energy here is the same, potential energy is going to cancel. I will end up only with the kinetic energy. Then this basically W is the work that this F net has done. Let's look at this F net. This F net is basically the difference between Fx and Ffk, and it points in this direction. So this one is F net x. If I want to look at the displacement vector, the displacement vector is also along the x. So this is delta R. So what is the angle between F net x that is doing the work and the displacement vector? The angle theta here between F net x and delta R, if I put those as vectors, as 0, right? Because they are overlap and in the same direction. So when I write here the work F net x times delta R times cosine theta equals to ek2 minus ek1 then this one becomes 1. Then I have, and since the speed at point 1 was 0, then the kinetic energy is also 0. So I have here F net x times delta r equals to half mv2 squared, right? Now I need v2, then v2 squared as 2 f net x delta r divided by m. If you substitute, you get v2 as squared up is 0.203, and v2 becomes 0.45 meter per second. 754 reads the following. A pen of mass 0.057 kilograms is sliding across a horizontal disk (25 centimeters). So the distance here, delta r, 25 centimeter, which is 0.25 meter. Its speed is 5.7 centimeter. What was the initial speed? So here at 0.2, 0.1, we need V1. We know V2 is 5.7 centimeter, or V2 is 5.7 times 10 to the power minus 2 meter per second. We need the initial speed. If the force of kinetic friction exerted on the pen by the disk is 0.15 Newton. Use conservation of energy. So here, we can see that the displacement vector is in this direction. So this is my delta r, and this is my friction, kinetic friction force. If we use the conservation of energy, then we know that W equals delta E. The potential energy between 0.1 and 2 is the same, so we have here delta EK, or we have FFK times delta R times cosine theta equals to half m v2 squared minus v1 squared. Again, the angle here, theta, between The displacement vector and the friction force is 180 degrees, as you can see. So I have 0.15 times 0.25 minus 1 equals to half 0.057. The mass V2, which is 5.7 10 to the power minus 2 squared minus V1 squared. So we have one equation, one unknown. If you work out the equation, what you're going to get is 5 equals 2.26 minus 5 minus 2.5 V1 squared. V1 squared is 1.32, and then V1 is 1.14 meter per second. Next question is 757. Reads the following. When an insect such as a flea jumps, the energy is provided not only by muscle, but also by an elastic protein that has been compressed like a spring. So not only the muscle, there's a protein also that helps with providing the energy. If a flea of mass 210 microgram jumps vertically to a height of 65 millimeter, so we have here the insect here at this point, jumping, getting an initial speed, jumping up, so it has its initial kinetic energy. This is my reference, zero potential, will jump all the way up 65 millimeter. It has a mass of 210 micrograms. If we know that 75% of the energy provided here is from that protein, comes from the elastic potential energy stored in the protein, determine the initial quantity of the stored elastic potential energy. Neglect energy losses due to air resistance. So we have here that insect jumping 65 millimeter up using the stored energy in the protein and the muscles. 75% comes from the protein, the remaining from the muscles. It has a mass of 210 micrograms. And yeah, we need to calculate this energy that this protein is providing to this insect. So what do we know here? We know that 75% of energy comes from the protein. This is my reference, and let's take this as my positive y. So the potential energy here at this point, because this is my reference, is 0. I only have kinetic energy. However, when this insect jumps all the way, reaches the maximum height, it comes to a stop, which means that the kinetic energy right at this point is 0. So if I write the conservation of energy equation here, EP1 plus EK1 equals to EP2 plus EK2. I said this is point, let me call this one point 1 and this one point 2. So in this case, EP1 is 0 and EK2 is also 0, which means that the energy here at EK1 equals to EP2. So by only knowing the height and the mass, I can calculate the amount of energy that was provided right here at point number 1. So EK1 equals to mgy, and EK1 has 210 micrograms, which means I have to multiply by 10 to the power minus 9 to make it kilograms, then 9.8, then the height, 65 to the power minus 3 to meter, and EK1 as 1.34 10 to the power minus 7 joules. Now, 75% of this energy is coming from the protein. This means E14 equals to 1.34 to the power minus 7 times 75%, and then E from protein as 1 and 10 to the power minus 7. Please. Okay, let's move on to the question 794. And 794, the question reads the following. Two men are dragging a boat of mass 57 kilograms straight across a level beach. Together they are exerting a force of 3.4 10 to the power 2 Newton at 21 degrees above the horizontal. The magnitude of the kinetic friction force on the boat is 2.9 times 10 to the power 2 Newton. Use work and energy to determine the speed of the boat after it has been dragged 2.3 meters if it starts from rest. That's almost close to what we have solved. Let's do this because it was requested. We have the mass as 57 kilograms. We have the force as 3.4 10 to the power 2 Newton. We have the 2.9. We have delta R as 2.3 meter. So this is point 1. This is point 2. The distance here is 2.3 meter. V2 is unknown. V1, starting from west. V2 is unknown. Delta R is in this direction, and the friction is in the opposite direction. So here, let's calculate we have here sigma F net on the x-axis is sigma of x. So we have here F net x equals to F cosine 21 degrees minus FFK. F net x equals to 3.4 cosine 21 minus 2.9. F net x is 27.42 Newton. Now this force is going to do a work where we have the work as delta EK. Again, the potential energy is the same. Then I have here F net x delta R cosine theta here. Theta here is the angle between the displacement vector and the F net. Now the F net, this is the projection. This is Fx. My F net is this. F net x is on the x-axis. And it is in the same direction as the displacement vector. So the angle here is 0 and cosine theta is 1 equals to half and V2 squared minus V1 squared. If you substitute 27.42 times 2.31 equals to half times 57 V2 squared, because we're starting from west. This guy is 0. Then V2 is 1.48 meter per second. So this is how we calculated the 794. The last question, 111. In this question, the question reads the following. A boy is playing with a rope tied to a tree near his favorite swimming hole, figure 743. Initially, the boy is stationary and the rope of length 3.7 meter makes an angle of 48 degrees with the vertical. He then lifts his feet slightly and starts to swing freely. If air resistance is neglected, use conservation of energy to determine his speed at the bottom of the swing. B, the maximum height relative to his initial position to which he can swing. So let's first draw the free body diagram here. So we have so this is 3.7 meter, 48 degrees. This is 0.1, 0.2. D1 here is 0. Actually, function. So this is my 0 level. Assume that this is my y. So what do we have here? We need v2. So we know v1 is 0. We know the length 3.7 meters. Theta here is 38 degrees. Okay, if we use the conservation of energy, we can calculate the height here before. So we know this height is 3.7 minus this, which is 3.7 cosine 48. So this height is 1.22 meter. I will need this one in my calculation for the potential energy at point 1. So using the conservation of energy, I know that EP1 plus EK1 equals to EP2 plus EK2. So for EK1, I'm starting from rest. V1 is 0, then this one is 0. Then I have EP1 as mgy1 equals to EP2. I have my mass is at the 0 level, then EP2 is also 0, right? So I ended up only with half mv2 squared. Now m can cancel, so I know v2 squared is 2gy1, and I also know y1 is h here, so v2 squared is 2 times 9.8 times 1.22, and then v2 squared equals to 23.91, and v2 as 4.89 meters per second. So this is A. B is determine the height, the maximum height. Definitely, since this system is a frictionless system, then definitely he will swing all the way up to reach the same height. So he will be reaching the same height.